So, hello and welcome to the 10th week TA session for the Statistical Mechanics course. Uh, so, uh, uh, my name is Parasar and I am a PhD student in physics at IIC Bangalore. So, yeah, let's get started with the problems. Yeah, so let's continue with uh, some examples and some problems on uh, Fermi statistics, the statistical mechanics of uh, Fermi particles or fermions. Yeah, so uh, let me just quickly check if, yeah, okay, that's all right. Yeah, all right, sorry. So, yeah, so like I said, we'll be discussing more problems on Fermi statistics. So, yeah, so let's look at this first problem. So there's an isolated system of non-interacting fermions. Uh, so let's say there's a container like this or a box like this, and there's a partition. Uh, and initially, the this system of fermions or this Fermi gas is uh, so it occupies this left half of the box, and then this partition is removed. So now the gas will expand into the full volume, and and the system is isolated. So this is a free expansion, like we have discussed many times in these TA sessions. Uh, so what we have to do is say something about the change of temperature of the gas in this process. So this partition is removed. So the gas undergoes expansion without doing any work. And also the gas is isolated, so it does not absorb any heat. And hence the internal energy of the system or of this gas is uh, constant during this process, or at least it's the same before and after the process. Yeah, so the internal energy is something that remains constant. And we have to understand what happens to the temperature. What is the change in temperature? Yeah, so we've discussed this before for classical ideal gas. So there we saw that the temperature does not change for an ideal gas, uh, and for a van der Waals gas, where the particles are weakly attractive, or the particles experience weakly attractive interactions among themselves. We saw that this free expansion causes cooling. So the main point is that the change in temperature in a free expansion depends mainly on the dependence of internal energy on the density. The density of particles. So let us call this little n. So the internal energy is in general a function of both the density and the temperature. The internal energy per atom, let's say, per particle. So little u is a function of both density and temperature in general. For a classical ideal gas, like we saw before, I mean, like we discussed before, um, the internal energy does not uh, change with density at constant temperature. So U is simply, so the total internal energy is simply uh, 3 by 2 NKPT. It may be more specific. So this U by N, okay, the internal energy per, let's say, number of particles. So yeah, so for a classical ideal gas, it is 3 by 2 kBT. So U by N depends only on the temperature. And we saw that for a classical, I mean, for a van der Waals ideal gas, the, this process of free expansion results in cooling because we saw that at constant temperature, the yeah, sorry, just a minute. Yeah, so for a van der Waals gas, so this has attractive interactions between particles. So there, as the density decreases, the internal energy will increase at constant temperature. As the particles move further apart on average, of course, their attractive interaction is not as strong as before, and hence at constant temperature the internal energy will increase. So for the internal energy to remain constant, the temperature will increase in this free expansion. All right. So just to revise the like the related questions we have discussed so far, and to be able to compare with what we are going to do today. Yeah. So today this problem is about Fermi gas. So it is non-interacting Fermi gas. So so let's say that, and it has been also given that we are at a temperature, let's say, much lower than the Fermi temperature. Yeah, so it is close to a degenerate Fermi state, as it is called. Uh, so let's look at what happens to the energy of this Fermi gas as a function of density. Okay, so let's say we're at t equal to 0, first of all. Then, even at t equal to 0, the energy does depend on density, uh, right? So that is because of the existence of Fermi C, and because it's a consequence of the Pauli statistics or of the Pauli exclusion principle. So you have a filled Fermi C, and so if this is PF, Fermi energy is, so this goes as yeah, n by v whole to the 2 by 3, because yeah, PF goes as n by v whole to the 1 by 3. Yeah, that's right. Yeah, so this is the Fermi energy, and the total energy of the in the ground state, E naught, So that is 3 by 5 EF. And so this also goes as n by v whole to the power 2 by 3. So it's uh, the particle density raised to the power 2 by 3. So as we keep on uh, increasing the density, as we keep jamming more particles into the box, the density will increase. And for a like for a degenerate Fermi state, the total energy will have to increase because of the Pauli exclusion principle. We'll have to keep occupying higher and higher energy levels as we increase the number of particles in the box. Uh, so as we increase density, the total energy of the ground state will increase. The system will have to pay energy uh, to uh, to have the particles very closer to each other. So uh, jamming particles uh, increases the total energy, or right. So this means that n increases. Yeah. So now this is at t equal to 0. Uh, so now let's say uh, we are at some small temperature, like non-zero temperature. So T is, let's say, positive but small. Yeah. So now let's look at how the internal energy depends on the density and the temperature. So we know that the internal energy, we have also uh, looked at this last time. I mean, how the energy behaves as a function of temperature at low temperature. Uh, so there is the usual ground state energy at t equals 0, and there will be corrections on top of this, obviously. So there's a correction proportional to t square, uh, and yeah, and the yeah. So I think it uh, goes something like this. So the total energy is E naught times 1 plus some some constants which involve pi and all, pi square by 12 or something. And here we have uh, yeah, I think yeah, something like this. Yeah. So oh no, no, so yeah, yeah, I think yeah, we can also just write this in terms of the Fermi energy. So yeah, so let's do that. So E naught is 3 by 5. Yep. So this is going to be yeah. So uh, this is how the energy depends on the temperature and the density. So the density goes into the EF, right? So we can write this as I mean, so when we write this, we have to keep in mind that the density enters this expression through the Fermi energy, and the relation between Fermi energy and density is this. So EF, the Fermi energy is proportional to n to the 2 by 3. Yeah, sorry. Uh, So we can then write this as some, so 5e by 3, let's say, is EF plus alpha t square by EF. Yeah, so in the free expansion process that we want to discuss, this energy is a constant. Uh, and we know because the gas is expanding, the density will decrease. So EF will decrease. So EF will decrease, and we have to find out what happens to the temperature T. Okay, so yeah, so uh, we can see that. So in this expression, the first term will decrease. So to compensate for that, the second term must increase. But there's also EF here. So to get the change, to get the sign of change exactly right, let us do something. Let's just take a derivative of this and set that to 0. So DEF plus alpha t square. Uh, so this thing is 0. Yeah. So we want the sign of dt. So 2 alpha t dt by EF is equal to alpha t square by square minus 1 into dEF. Yeah, so remember we are at a temperature much less than the Fermi temperature. So T is so this alpha has a kb kb square, right? So T is much less than EF. So that means this term will be negative, and this term is also negative. DEF is negative. Yeah, so that means uh, there must be an increase in temperature of the gas in this process. Yeah, okay. So how do we understand this, qualitatively, without doing this calculation? So remember, if there are some so so if we go back to the van der Waals gas, the classical van der Waals gas, there we saw that uh, the we saw that the temperature will decrease in a free expansion, and we said that it is due to the effective attractive interactions between the particles. And in an ideal gas, the temperature doesn't change because there are no interactions between the particles. Here we have fermions, and even though these are not interacting, uh, the 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 fact that we have non-trivial uh, particle statistics. So we have fermions, and uh, just from the fact that we have fermions, uh, we can say that there'll be some effective kind of repulsion between these particles. The particles will want to be away from one another. So they will feel some sort of effective repulsion, and that can be, this can be used to understand the fact that we have uh, the gas, this temperature increasing in a free expansion. So this can be the fact that you have delta t greater than zero, this can be uh, yeah, this can be thought of as arising from some sort of effective repulsion between the particles. Okay, so all right. Okay, let's move to the next problem. Uh, yeah, so in the rest of these problems, we are going to uh, just a minute. Yeah, so in the rest of these problems, we are going to look at some very interesting examples. Sort of you can think of as uh, 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 using whatever we have learned to various systems to understand various phenomena and various types of materials. So so it's going to be very interesting. So in this problem, we have a model of a semiconductor. Okay, so you might have heard of a semiconductor as uh, being a material with some gap between the uh, valence and the conduction bands. Yeah, so we're going to look at uh, one such model. I mean, like a model which will capture this feature and try to explore its properties. Yeah, so it's just a simple model that will capture the essential features of a semiconductor, like the conductivity, specific heat, and all. Okay, so the model is like this. So like promised, we have uh, a conduction band and a valence band. So this dashed line is the zero of energy, and there is a set of states, a continuum set of states here below and above the zero level. Okay, and uh, the energies of these bands are given. So so each band has some width W. So that is the extent in energy uh, that is occupied by this band. Uh, so each band has bandwidth W, and there's a band gap between uh, these two. I mean, there's a gap between these two bands, which is equal to delta. Okay, so the energies of the lower band, they uh, they go from uh, let's call this valence band, the lower band. So the energies go from minus delta by 2 minus W to uh, to minus delta by 2. And similarly for the conduction band, the energies go from delta by 2 to delta by 2 plus W. Okay, and the like the simplicity of this model is that uh, the density of states in each of these band is constant. It's constant with respect to the energy of the level of the state. So so each band has constant density of states. So remember, this is a continuum of energies, energy states, uh, and the density of states is a constant across the band. So we can think of this as coming from some uniformly spaced, like a large number of like a very large number of uniformly spaced states. giving rise to this constant density of states. And this density of state, uh, the density of states is d per unit area. So, so remember the density of states is proportional to the volume. So here we have a two-dimensional system, so it's proportional to the area. And so there are these bands. So there are these energy states, single particle states available for the electrons for each spin variable. Okay, so there are these states uh, for for a spin up and also for the spin down. Okay, so there are actually two valence bands and two conduction bands, one for each spin. So actually there are two valence bands, and I mean it's generally not stated like this, but yeah, for the sake of clarity, let me say this. Yeah, so this is about the energy levels, the single particle energy levels that the electrons can occupy. And next comes the information about the filling. So it is also given that these so the system or these bands have to be filled with any number of electrons such that at t equal to 0, so at t equal to 0, the valence bands are completely filled. Both, of course, both the spin up and spin down. Yeah, so that is the setup given in the question. I mean, so we have discussed the single particle energy states and the number of electrons, the filling of the system. Yeah, so now, yeah, coming to the first question, uh, it's about the relationship between the variables defined here. Yeah, so let's see what this like what it means to fill exactly the valence band at zero temperature. Okay, so there are any number of electrons. So let's look at the number of states in each band, first of all. Okay, so number of states in each band is the density of states, which is d times a times w, the width of the band. We can do this simple multiplication because we have constant density of states. So this is per spin. So at t equal to 0, the valence bands are completely filled, those of both spins. So Ne, the number of electrons at t equal to 0, should be twice of this. Yeah, so this valence band is completely filled. Uh, yeah, let's draw a separate picture. Uh, so all whatever. So if you can think of these as a very large number of finely spaced states, then all of these are occupied. Yeah, and all of these are empty. Yeah, maybe I should just simply draw two lines. Yeah, so all these are occupied and all these are empty. And we have any number of electrons here. Okay, so uh, So we should have these many number of electrons uh, to completely fill the valence band. Okay, so yeah, now comes the interesting part. Uh, yeah, so basically we have to find what the chemical potential of the system is and the number of electrons in the valence and conduction bands. Okay, as a function of temperature. Yeah, so now we should think about like calculating like all the usual stuff. What is the chemical potential? What is the specific heat, energy, and I mean, what is the energy, specific heat, all these things. So, I mean, first we have to start with chemical potential because, uh, like we have discussed many times, yeah. So, in the grand canonical ensemble, uh, we have to find the chemical potential uh, so that the mean value of the number of particles is what we want. So yeah, let's start with this particle number equation to find mu. So which says so on the left hand side is the integral over all the energy values. So we have multiplied the density of states with the occupation and occupation number and integrated it over the entire energy spectrum. So that should be equal to the mean number of value, the mean number of particles. And this is given to be Ne. Okay, so in this problem, yeah, in this problem, the density of states looks like this. Let's try to plot the density of states. Yeah, so it is the density of states is non-zero only in these two windows of width W each, and zero elsewhere. So this value would be 2 2 dA, 2 because we have again up and down spins. So our integral in this case would look like this. Um, so this is equal to Ne, which is 2 dAW. Yeah, so in principle, we have to solve this integral. I mean, we have to do these integrals and solve this equation to find mu. But here actually, and in fact, this integral is something that can be done exactly. It's simply e to the x, e to the x plus one. I mean, so it's just a linear combination of e to the x and one in the denominator. So this integral can be done exactly. But we'll see that there's a cute trick or a nice result which we can use to completely bypass doing these integrals. Uh, So the trick is that uh, so first of all we are at half filling. So what that means is the number of electrons in the system is half of the maximum number of electrons possible. So in the grand canonical ensemble, if we let all the electron states be occupied, that would be the state with maximum number of electrons. So of course, here we are assuming that the energy spectrum is bounded from above. If that is the case, we can have this notion of half filling or filling, and half filling is something when this filling is half. The fraction of states occupied are or the number of electrons that are there in the system is half of what would be the maximum. So let us, in this case, see what the maximum number is. So in this case, it's very clear. Uh, so we can occupy both valence and conduction bands of both spins. That would be the maximally occupied state. So maximum number of electrons uh, is simply 2 times dA. But number of electrons we have is just 2 times dA. So we are only occupying the valence band exactly. So obviously it is at half filling. So when this is the case, when we are at half filling, and uh, also that comes to our rescue in this case is the fact that we have a symmetric density of states. So there's a zero energy, and the the set of available states is kind of symmetric above and below this energy value, right? So that can be more concretely stated uh, as the following: uh, that the density of states is symmetric about zero. So that means G of E is equal to G of minus E. So this can happen, for example, if there is a state with energy minus E, for every state there is with energy E. Okay, so which is indeed the case here. So our density of states is indeed symmetric about the zero uh, energy value, uh, and when we have these two conditions met, the claim is that so half filling together with so this means that the chemical potential is zero at all temperatures. So this is the claim. Uh, so the claim is that we need not actually work so hard to calculate the chemical potential in this case. It is simply zero at all temperatures. Yeah, so let us see why this is the case. Yeah, so let's see why this is the case. Uh, we'll try to prove this we'll try to show this like in general. So So the total number of electronic states is simply the density of states integrated over the entire energy spectrum. So when we say we're at half a length, that means uh, the expected number of particles is half of that. So it will be equal to this. Okay, and let us now look at the particle number equation. So the expected value of number of particles. This thing will be integral. Okay, so now we can, uh, I mean, to be able, sorry, excuse me. Yeah, to be able to use this uh, symmetric property of the density of states, we can write this integral uh, like this. So we have done nothing. We've just written the integral as uh, the sum of these two intervals. And so here we can make a change of variable, e going to minus e. Yeah, so that will change this to 0 to infinity dE, g of minus e, which is actually g of e. Yeah, this is where we have used this the symmetric property of density of states. Yeah, so now we can write this integral as yeah. See, this is nothing but one. Yeah, so this is whatever is there in the brackets is it is identically equal to one. So the number of sorry, yeah, sorry. Let me be more careful. Yeah, uh, so here we would have minus beta into e plus mu. Yeah, sorry, I have forgotten to include the chemical potential. Uh, oh, yeah, which we are trying to show is zero. Yeah, so this will be the particle number equation. Let's uh, let's go one step back. Yeah. So our particle number equation is this. So number of particles is this. So this must be equal to half of uh, integral minus infinity to infinity g of e. But g of e is even function, so that can also be written as integral 0 to infinity d of e g of e, d g of e. Yeah, so this is the particle number equation which we want to solve for mu. So our aim is to solve this for mu. But let's make an observation here. If we substitute mu equal to 0, then this uh, uh,
then it will automatically satisfy this equation. So mu equal to 0 is always a solution for this equation. Yeah, so yeah, there will be a unique solution always. I, yeah, so mu equal to 0 is always the solution for this equation. Because let's just put mu equal to 0 in this equation and check if it is true. So if you simply put mu equal to 0, you will get sorry, there's a minus here. Yeah. So which is simply equal to, yeah. So I mean, this factor is this is identically equal to 1. Yeah. So we have what we want, which is simply, yeah. So mu equal to 0 gives rise to half filling, like we saw. So this is half the number of particles, which is what we want. So mu equal to 0 is always it's always true, uh, regardless of the temperature. Yeah. So to go back to this question, the answer to this question is the chemical potential uh, mu is equal to 0 for all temperatures. Okay, so let's now look at uh, okay. Yeah, okay. Let's look at the number of particles in valence and conduction bands. So let's say it is NV. NV is going to be equal to, and the number of particles in the conduction band is this. Yeah, so we can actually do these integrals exactly. Yeah, so let's look at one. I mean, yeah, so this will obviously be equal to Ne minus Nv. So they must sum to the total number of electrons. So it's sufficient we calculate for the first one. So yeah, so let's actually calculate the number of electrons in the conduction band Nc. Sorry, and the number of electrons in valence band would then be this. Yeah, so to do this integral, let's start by making the integration variable dimensionless. Yeah, so integral dx by e to the x plus 1. Um, yeah, I think you can do something like e to the x plus 1 is equal to t. Yeah, I think so. Yeah, so that will give uh, e to the x dx is dt. So this is going to be, yeah, something like this. Yeah, so this can be calculated. So this is, yeah, I think it is something like 1 by, yeah, log t minus 1 by t between these two limits, or log 1 minus 1 by t between these limits. So that will be equal to, did I get the limits right? Yeah, I think so. Yeah, so this will be, yeah, so doing this integral, yeah, yeah, so the lower limit will be something like this. Yeah, so uh, what you can try to show is, I mean, do this integral, and what you will then see is that the number of electrons in the conduction band, so this grows with temperature, this increases with temperature, uh, and increases with temperature as this. So, so this means that the conductivity of semiconductor, uh, will increase with temperature. Okay, so it is actually suppressed. Uh, uh, so the number of electrons in the conduction band, that is exponentially suppressed in the ratio of gap and temperature. So actually, as you increase temperature, this increases uh, very quickly. And yeah, so this is this nature of conductivity increasing with temperature is that is to be contracted with uh, the the nature in which the conductivity of a metal decreases with temperature. So here, for a semiconductor, we have a band gap, like a finite non-zero energy gap uh, between the highest level in the valence band and the lowest energy level in the conduction band. So because of this finite non-zero band gap, uh, the occupancy in the conduction band uh, is actually very less and like negligible at low temperatures. So as you increase temperature, the occupancy of this band will increase, and then you'll see that the conductivity increases. Yeah, so that is the that's how the number of electrons in the conduction band depends on temperature. Yeah, so in the interest of time, I'm not completing the simplification and uh, further mm, uh, further analysis of this formula. Yeah, so please do this integral and try to get to this. Of course, there'll be other factors involving W and all, but the main uh, like the main factor that we are interested in is this. Yeah, so try to show that. Okay, and for the next problem, yeah, sorry about that. Yeah, for the next problem, let us quickly try to uh, see how the specific heat capacity can be calculated for this model of semiconductor. So the energy, let's first calculate the energy. The energy is going to be, yeah, let me just write it like this to simplify, I mean, to save some time. The integrand is the same anyway for both these integrals. Yeah, so notice I'm not writing mu here because I mean we have discussed that mu is 0, so we can just set it to 0. Yeah, so now oh yeah, sorry, of course, yeah, there is E here because we're calculating expectation value of energy. Yeah, so we can do some I mean we can play around with these integrals and try to see how to simplify them. Yeah, so for the first integral, again, let's make a change of sign, change of variable, uh, which goes like this. So the first integral would then be so let us bring this out, this factor. So this would be the first term, and the second term, I mean, let's it is it is what it was. Yeah. So this, yeah. So we have just made the integration limits the same for both the integrals, and this will be then equal to this can be written like this. Yeah. So this will be sine h of beta e by 1 plus cos h beta e. Yeah. So using some uh, hyperbolic trigonometry formulae, we can, I think, finally write this as uh, yeah, some tan h beta e by 2. No, so tan h, yeah, tan h of this. And there was some minus, yeah, so there is a minus sign here. Yeah, so now let's just quickly verify this, I mean, in some limit. So when t is 0, this beta goes to infinity and tan hyperbolic at that is simply 1. So the ground state energy would be simply minus 2dA into delta by 2 to delta by 2 plus W dU. Yeah, so this is just the energy corresponding to filling the valence band completely. Yeah, so this looks okay. Yeah, so now for a general temperature, oops, sorry. Yeah, mm, okay, let's do this. Yeah, so we'll get this. So yeah, I don't know how to do this integral for I mean for this function. Exactly, yeah. So I don't know if this can be written in some closed form. involving only logarithms, exponentials, and so on. I mean, without involving these uh, polylogarithms or like this Fermi-Dirac functions. But we can still try to understand the low temperature behavior. So let's say, yeah, so physically, uh, what we are looking at is a gap here. And let's say our temperature T is such that T is much, much less than delta. KBT is much, much less than delta. So that means beta delta is much, much greater than 1. So if you look at the limits of this integration, those limits are like very large numbers, large real numbers. In the limit we are interested in. So we can expand tan h x by 2 uh, for x very large. I mean, we can include corrections to this, and from that we can extract the low temperature behavior. Yeah, so let's see that. I mean, let's try to uh, get a expansion for tan h x by 2 for large values of x. So tan hx, let's just do it for tan hx or tan hy. So this is defined like this. Yeah, so for large y, so we're interested in y very, very greater than 1 in this regime. So that would be something like um, 1 minus e to the minus 2y by 1 plus e to the minus 2y. Yeah, so now we can expand this. Since y is large, e to the minus 2y will be small, and we can expand in terms of that. So this would be 1 minus e to the minus 2y plus e to the minus 4y plus dot 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 dot. Yeah, so it is 1 minus e to the 2y, actually minus 2 times e to the minus 2y plus dot dot dot. So the first correction after 1 is this. So yeah, e to the minus 2y is a very small number. Yeah, so this is the correction. I mean, this is expansion of tan h. And we can put this here in this integral to get the specific, to first of all get the energy. So it's going to be integral beta delta by 2 to. So tan hx we can replace with uh, so tan hx by 2 we have. So that will be 1 minus 2 e to the minus x. Yeah, so this first term where we have I mean this first term when this is what we calculated before for the ground state energy at zero temperature by replacing tan h with 1. So this term will give you the ground state energy. So this is E naught at equal to 0 plus 4 dA by 2 square. Yeah, so this would be the integral we have to do. Yeah, so this can be done. This can be done by integration parts, I guess, easily. And so we can get this the first leading term. Uh, yeah, so again, due to the time constraints, I will not be able to do this here. But yeah, this integral is fairly simple, I think, and you can get the this first correction term to the energy, and then we can calculate the specific heat capacity, the heat capacity like this. So this is the term that will give uh, the first non-zero contribution. Yeah, uh, so yeah, please do this integral uh, and and calculate the heat capacity. So, but let me discuss what you would get. So you will see that the heat capacity will go again as so it will be suppressed exponentially in the ratio of the gap to the temperature. Yeah, so since there are no states immediately available for the electrons to jump into, so there are no states immediately above the valence band for the electrons to jump into and hence absorb energy. Yeah, so they cannot absorb like a lot of energy because there's a band gap and hence the specific capacity is exponentially suppressed. And contrast this with a metal. So last time we saw that. So this is for a semiconductor. And now for a metal, we saw that uh, the specific heat capacity is linear in temperature times the density of states with Fermi energy. So for a metal, you'll have a non-zero density of states uh, at the Fermi energy. Finite, okay, let me say non-zero. Non-zero density of states at the Fermi energy. So uh, you have linear dependence of heat capacity on temperature for metals. Yeah, so like we discussed last time, this can be understood uh, as due to there being uh, there being single particle energy states uh, like immediately above the Fermi energy for the electrons uh, which absorb the energy to hop into. So they can uh, yeah so they can absorb heat better compared to let's say a semiconductor where where the next available energy level is much higher. Yeah, so you can ask, I mean, why does this formula not apply for semiconductors? I mean, whatever we discussed last time. So first of all, the density of states at the Fermi energy or the chemical potential at T equal to zero, that is simply zero for a semiconductor. So this expansion that we did there would not work. Yeah, so uh, and like we discussed, the calculation that we did last time for the specific for the heat capacity of metals that relied on the assumption that uh, there's a continuum set of states with non-zero density of states immediately above the Fermi energy. But for a semiconductor, that is not the case. Uh, you have chemical potential right in the middle of the band, mu equal to zero. So chemical potential is So that is between the bands, and the density of states there is simply zero. Like there are no states there, right? So yeah, so this is the difference, the qualitative difference between the heat capacities of a metal and semiconductor. Yeah, so this is just a simple, even though it's a simple model of semiconductor, it includes the most important feature of there being a band gap between the valence and conduction bands, and that is enough to capture most of these important properties. Yeah, so okay, so all right, okay, so let's move to the next problem. Yeah, so this problem is not something that will teach us like about some phenomena or something, but just mm, just a nice problem to get ourselves familiarized with doing these integrals and all. So in this case, it turns out that in this particular problem, it turns out that a certain integral can be evaluated exactly. So it's like a nice instructive exercise to do. Uh, yeah, so let's do that. Uh, yeah, so this problem is, oops, sorry. Yeah, so this problem is about fermions confined to move in two dimensions. So it's a two-dimensional system, or it's so you can confine electrons so that they effectively move only in two directions. Uh, so it's a 2D system of fermions, and the single particle energy states, the kinetic energy single particle is given by the usual non-relativistic dispersion. Uh, so it is quadratic dispersion. So the question is about finding chemical potential exactly as a function of temperature. Yeah, so it turns out that in this case, I mean, for this the combination of dimension and dispersion, the density of states is a constant. Okay, so like we've discussed in the previous weeks, the density of, so if you have if you're in d dimensions and you have a dispersion which goes as mod k to the power m, then the density of states g of e goes as e to the d by m minus 1. Yeah, so we looked at this before. So in this case, what that means is that g of e uh, is proportional to e to the 2 by 2 minus 1. So it's a constant. So the density of states is independent of energy, just like the toy model problem that we discussed pre in the discussed just now previously. So in the semiconductor toy model problem, yeah. So there we could assume that the density of states was constant. Yeah. So here also for fermions in two dimensions dispersing according to the quadratic dispersion, the density of states is also constant. So yeah, so it turns out that we can do this do a certain integral exactly because of this. Yeah, so Yeah, so let's find an expression for the density of states in terms of density in terms of the particle density with all the factors. Let's quickly do this. So omega is h bar square k square by 2m, and constant energy contours would be circles. So the number of states in this thin annulus would be a by 2 pi whole squared times times 2 pi k dk, where a is the area of the system, the two-dimensional area of the system, and so this is number of states uh, just a by 2 pi k dk. So d omega is actually h bar squared by m k dk. Yeah, so this is actually this is okay, yeah, this is E. Um, the density of states G of E, like we said, is a constant, like a discussed as a constant, and uh, when we uh, when we take into account the spin as well, uh, so there's a spin of particles, so that would bring in a factor of 2. The density of states would be am by pi h bar square, where A is the area of the system. Yeah, so now let's try to solve the particle number equation and find chemical potential exactly. So how much time do we have? Okay. Yeah, so mm, yeah, so this is the particle number equation, and yeah, you can see it is already you can already see that this integral can be done exactly because yeah, we encountered a similar integral before and we were able to uh, solve this integral. Uh, yeah, so if you make this substitution, yeah, so yeah, we can do this integral again if we want, or the notice that this is the Fermi-Dirac uh, integral that we discussed last week at n equal to 1. Yeah, uh, so you have x to the 0 here. So this is the definition of f1 of z, and f1 of z is actually equal to log 1 plus z. Yeah, so we have this expansion for f1 of z, and so on. So this is nothing but log 1 plus z, I think. Yeah, yes. Yeah, so then we can write, this is equal to log 1 plus uh, e to the beta mu, or yeah, and yeah, so from this we can just find the chemical potential as so this is an expression for mu, chemical potential. Yeah, so in this case, because the density of states was constant, we could just do this exactly, and yeah, it's just uh, yeah, it's a simple integral, and there's a problem which just illustrates that. Uh, I mean, so this is what we would like to do uh, for like let's say uh, for for any problem, but of course it's not possible to get a closed form expression for everything. But here it's yeah, you can actually see study how the chemical potential depends on temperature. You can plot this and see and get some feel for it. Okay, all right. Yeah, so moving on to the next problem. Okay, yeah. So this problem tries to uh, tries to teach us about the magnetic phenomena of for Fermi gas. Okay, so yeah, so we have done problems on magnetism before. Uh, Problems where you know we you have uh, uh, you have sites where spins can sit, uh, like yeah, and some external magnetic fields applied, and studied magnetization of the system, for example. So here okay, in the previous in the previous magnetic like in a, yeah, in the previous discussions of magnetism, the objects carrying the magnetic moment were distinguishable, like localized spins or moments, where you could like associate each, let's say, spin to a site, so that there was a localized distinguishable degrees of freedom carrying the magnetic moment. But here it is, here we have the gas particles. So we have like a Fermi gas. So we have a bunch of fermions in a box. So these definitely are not localized. Uh, so I mean, as we have learned and applied all the formalism so far, yeah. So these are uh, indistinguishable in indistinguishable particles carrying the magnetic moment. Mm, distinguishable, yeah, carrying as opposed to localized. Yeah, so yeah, let us see what applying a magnetic field to a system of Fermi particles will do. In particular, let us calculate the magnetization and see how to describe the state of the system. Uh, yeah, so let's say we are at zero temperature. So let's do all this at zero temperature. That is already interesting enough. Yeah, so the effect of magnetic field is to induce a, I mean, uh, is to couple to the spin of the electrons, or fermions, such that the spin up state for each particle will have a lower energy than the spin down state. So there is a splitting of energy for the two spins by this Zeeman-like interaction. So energy will be the magnetic energy will be minus mu b for up and plus mu b for down. Okay, and uh, each particle will uh, I mean, so this is true for each particle. Like if a particle is in the upspin state, or there's a particle. Okay, let's be more concrete. So the single particle states can be labeled by k bar and s. So we have to specify obviously the momentum and the spin of the state, and the energy of this state is this. So hopefully it is clear. So all the single particle states with upspin have a lower energy compared to the single particle state with the same momentum and down state. Okay, so now, so we are at t equal to 0. So uh, describing the state is describing the full state of the system. Sorry, yeah, describing the full state of the system is it's simple enough. So we have to fill all the uh, you know t equals 0. So fill all the energy states below some Fermi energy. Yeah. So let's look at what the situation is when B is equal to 0. So when the magnetic field is 0, so this is a Fermi surface for up spin, Fermi surface for down spin. Yeah. So even though they may look different, I mean that's on me. Yeah. Okay. So these are the same size. Let's believe that. Uh, yeah. So this is what we have at B equal to 0. So both of these radii. So if you keep track of what states are occupied, which have a up spin label, and also track what states are what momentum states are occupied uh, for states which are labeled by a down spin, you'll see that the Fermi momentum for both of these is equal. I mean, why not? Because yeah, so if one were higher, then you could uh, transfer particles from one to the other to decrease the energy, right? So here the Fermi energy for both of these is equal. But when you have applied some magnetic field B, because uh, because it is favorable for the particle to be in the up state. More it is possible that more particles would want to be in the up state. So yeah, we'll shortly calculate by how much and all. So because uh, the upspin states enjoy a lower energy, so you can have different Fermi momentum for both these states, for both the spins. Okay, so uh, let's try to find what PF up and PF down will be as a function of the magnetic field. Okay, so what we know is that ultimately both of these surfaces must terminate at the same energy, right? So PF up square by 2m minus mu times B should be equal to PF down square by 2m uh, plus mu B. Yeah, so yeah, so we can see that PF up square minus PF down square by 2m is 2 mu B. So indeed, so PF up will be greater than PF down. Okay, so but still, I mean, we don't have enough equations as of now to find both PF and P down. What is the other information we need? We need to put in. So it is that both these Fermi momenta have to be such that total number of particles is equal to what we want, right? So if there are n number of particles, so n will be equal to uh, sorry, yeah. So there are n number of particles in total, so this should be equal to n up plus n down, where n up and n down are the number of particles in the up state and down state, respectively. Yeah. So this is going to be integral 0 to EF. Yeah. Okay. Integral. Yeah. Integral minus infinity to infinity. dE. Uh, yeah. So let's actually look at how the density of states looks when you have a magnetic field. So this is energy. Sorry, this is density of states, and this is energy. So actually, when you have a magnetic field, the up state's energy can be as low as minus mu b. Okay, so there is this minus mu b here, below which there's no state with that energy. So this is minus mu b, and from here you can have uh, states with energy above this and above this. Okay, and this goes as square root e, the standard square root e for the quadratic dispersion in 3 dimensions. This is the up band, or let's say the upset of states, and then you have plus mu b, below which there is no energy state with downspin. So this would look like something like this. This is for the down band or the down states. So this is not the total G of E. So this would be G up of E. So this curve is for G up of E. This curve is for G down of E. Okay, and let's say the Fermi energy is somewhere here. So let's say this is the Fermi energy, which is equal to, yeah, let's just call this some EF. Right. So now we have, yeah, so when we're at zero temperature, all the states to the left of Fermi energy in this diagram will be occupied. So the number of particles in the up state will be integral minus mu b to EF dE uh, square root of yeah, or yeah, we can also just write this as, yeah. So integral, it will be 0 to mu b plus EF dE square root of E. Yeah, times of course uh, the 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 proportionality factors. So this is proportional to square root E. As you uh, okay. So this thing is proportional to square root of E plus mu b. Okay, and this thing is proportional to square root of E minus mu b. Yeah. So when we we have this just don't have the square root of E. I mean, we also have these factors. Uh, let's just call it some alpha. Alpha times the volume, because the density of states is proportional to volume, and n down is again alpha v times integral 0 to EF minus mu b dE square root E. So yeah, so if you're confused about this, so this is nothing but just integral minus mu b to EF dE square root of E plus mu b. So when you make a change of variable, uh, you can bring it to this form. Yeah, so hopefully this picture is clear enough. So we are integrating from minus mu b to minus mu b to the Fermi energy EF, the density of states for the up band or up state of states. Okay, and uh, yeah, and when you make a change of variable, you can also write it like this. And similarly, this is mu b to EF. Yeah, so these are the number of up and down states, and when B is equal to 0, obviously both of these will be equal, and of course both the Fermi momentum will also be equal. But yeah, let's see what we get for a non-zero B. So yeah, it's a simple integral. So this is going to be EF plus mu B whole to the 3 by 2 is 2 by 3, and down is going to be, yeah, so we want n up plus n down to be equal to uh, yeah, so we want this to be equal to the total number of particles. Uh, so we have to find we have to find the Fermi energy from this. So this will fix the Fermi energy. And then we can use, the relation EF is EF up squared by 2m minus to find each of these Fermi momenta, Pf and P down, Pf up and Pf down. Yeah. So uh, what we have as the result is, so we can already clearly see that both of these cannot be equal. N up and N down they have to be different, right? Because uh, yeah, because I mean we can clearly see that N up is greater than N down. So what that means is that since the number of particles occupying the up states in total is greater than the number of particles occupying the down states, we have a net magnetization or net magnetic moment. So the magnetic moment will be mu times n up minus n down. So that will be equal to uh, yeah. So this is the net magnetic moment, and we have or if you want the magnetic moment per unit volume is equal to that. Yeah. So we can see how this depends on the magnetic field. Uh, so for this, uh, we can do so we can assume that so in the limit mu b is much smaller than EF. So both of these Fermi surfaces for up and down spin separately, they change only like slightly compared to what they were originally. So in this limit, we can do an expansion of this to find to let's say uh, to get a more uh, simpler looking dependence for small magnetic fields. So in that case, we can write yeah, and then we can just expand this in the small parameter mu b by EF. So that will give us something like 3 mu b by EF. Yeah. So then finally this will be 2 mu alpha square root EF times the magnetic field B. So this is the magnetization. Uh, so of course, technically, so this EF also depends on the magnetic field. Uh, so that will be determined by this equation. Yeah, this equation. Uh, so this equation will determine what the Fermi energy is. So yeah, so to leading order, so of course you'll will have a constant we'll have a constant which is the Fermi energy when B is equal to 0, plus maybe some linear correction to that in B. But uh, to get the most important uh, term here, the most important contribution here, we can simply replace EF with the value of EF at magnetic field equal to 0 because uh, the corrections to that EF will only give rise to higher powers of magnetic field. So if you are interested only in uh, let's say the derivative of the magnetization when the magnetic field is 0, so this is called the susceptibility. Yeah, so this is going to be equal to, yeah. So this is just the Fermi energy when you have no magnetic field. Yeah, to calculate this derivative at b equal to 0, that term is sufficient. Yeah, so indeed, so we have seen how the Fermi gas becomes magnetized when you uh, I mean how the we have seen how the Fermi gas acquires some magnetization when you apply an external magnetic field. So what happens is uh, there'll be some electrons, or there'll be some electrons uh, that will leave the down states, like the spin down states, and it would be favorable for the entire system for lesser number of downspin states to be occupied than the number of upspin states occupied. So it is not like so notice that it is not that the entire system, like it is not that all the particles are in the upspin state. So if you have, let's say, uh, localized magnetic moments, and you're at t equal to 0 and just apply some magnetic field, let's just say you have some non-interacting localized magnetic moments at t equal to 0, and you apply some magnetic field, then of course all the spins, all the magnetic moments will go to the upspin state. But of course that is not the case here. Uh, uh, if that were to be true, the system will have to pay a huge amount of energy to to accommodate all the particles in a single spin band. Let's say the upspin band. So that is obviously not favorable. What the system does is some of the particles uh, that were in the upspin state would sorry, some of the particles that were in the downspin state would now be occupying the upspin states. Okay, so this is another example another problem where we saw some interesting phenomena involving fermions. Okay, so uh, yeah, I think that's all I have for today. Yeah, so let's meet next week, and I think next week uh, we're going to be discussing some problems on boson statistics and the thermodynamics of Bose gases and Bose statistics. Okay, all right. See you then.